In section 11.2, we are going to look at derivatives of exponential functions. First of all, I want to remind you what an exponential function is. It is one in which the variable is in the exponent. And probably the most common exponential function that you have seen is e to the x. That's what we are going to look at first, is how to do the derivative of e to the power. So the derivative of e to the u is e to the u. First thing you do is just write down e exactly as it was given to you. And then you take it times the derivative of the power. In our first example, we are just going to find the derivatives of the various functions of e. And the first one, a, is y equals 3e to the x. When you are finding the derivative and you have a coefficient like we do here, remember that you just keep the coefficient. Now, for the derivative of e to the x, you write down e exactly as it was given, times the derivative of the power, which is 1. So this just becomes 3e to the x. Hopefully what you noticed here is that the derivative of e to the x is e to the x. On example B, our function is f of x equals e raised to the x to the fourth power. So follow the rule to do the derivative. F prime of x, first thing you do is write down the e exactly as it was given to you. Now you take it times the derivative of the power, which will be 4x cubed. It's not wrong to leave it this way, but typically what you'll see is anything that's not the e written out front with the e at the end to make it clear what's the power and what's not. On example C, we have y equals e raised to the natural log of 2x power minus e to the x. Before we do this derivative, we need to look at a log rule. A raised to the log base a of x equals x. When you have a logarithm as an exponent that is the same base as the base of the exponent, the effect is that they offset each other, they cancel each other out, if you will, and what's left is just the argument. So before we even begin the derivative on C, we need to recognize that a natural log is a base of e. So we have an exponent that has a base of e, and the base of the exponent is e. So, if you will, these two cancel each other. It's not really canceling, but that's what we like to say. So it's left with just 2x minus e to the x. The only thing that's left when your base of the log and the base of the exponent match is the argument of the logarithm. Now this is an easy derivative to do. The derivative of 2x is 2, and the derivative of e to the x is e to the x. I just noticed as I was typing this that there are 2 letter C's in example 1. This is the second letter C, we'll call it D appropriately. Our function is the natural log of the argument e to the 3x minus 4. Because the outside item is a natural log, when we do this derivative, we have to do the natural log rule first. And that rule tells us to do 1 over the argument times derivative of the argument. Derivative of e to the 3x will be e to the 3x, just write down the e, times derivative of the power is 3, and then the derivative of the minus 4 is 0. So doing this multiplication and making it one fraction, we will have 3e to the 3x over e to the 3x minus 4. Some of you might be tempted to cancel that e to the 3x. You cannot cancel here because what's happening in the numerator is multiplication, which would be okay for canceling. But in the denominator, you have subtraction. You cannot cancel when you have subtraction. So this is your final answer. On example E, we have y equals the quantity of e to the 9x minus 3 being raised to the 4th power. What you need to recognize on this one is because we have the entire quantity to the 4th, this is a chain rule question. We're going to have to use the chain rule. We will do the derivative of e when we do the derivative of the inside, but the entire problem requires the use of the chain rule. So remember that the chain rule says, take the power to the front, leave the inside exactly the same. So we have e to the 9x minus 3. Now go down by 1 to the 3rd power. Now do the derivative of the inside. The derivative of e to the 9x, write down the e exactly as given, times derivative of the power is 9, and then the derivative of the minus 3 is 0. To pretty this up a little bit, make it look nicer, we're going to take the 4 times the 9, and we're going to move the items that are single items all out front. So it's going to become 36 e to the 9x times the quantity of e to the 9x minus 3 being raised to the 3rd. The last item in example 1 has the function g of x equals e to the negative 5x power times the natural log of x squared. Because there is multiplication understood to be happening between the e and the natural log, what you need to recognize then is that you need to use the product rule, where the e to the negative 5x is your first and the natural log of x squared is your second. So to do the derivative of this function, we're going to write the first exactly as given times the derivative of the second. The derivative of the natural log of x squared is going to be 1 over x squared, 1 over the argument, times derivative of the argument, which is 2x. So now there's our first and derivative of the second. We add to that the second as given times derivative of the first. Well, we're going to write down the e exactly as given and take it times derivative of that power, which is negative 5. In looking at what we have now, the plus sign separates into terms. So everything before the plus sign is term 1, and everything after the plus sign is term 2. The reason I'm having you look at that is that I want you to see that e to the 5x, negative 5x, shows up in both terms. So we are going to factor out e to the negative 5x power. So if we do that, we'll pull e to the negative 5x out front. What's going to be left inside will be 2x over x squared after taking the e to the negative 5x out of term 1, taking that same item out of term 2 will leave us with negative 5 natural log of x squared. Well, this can be simplified a little bit more. Leave the e to the negative 5x out front. 2x over x squared, we can simplify that to just be 2 over x. And then because this is plus and then a negative, we can write minus. And the other thing that you can do, but you don't have to do, is drop the power on the argument times the 5 out front and write it as minus 10 times the natural log of x. And then this is about as simple as your answer is going to get. If you have an exponential function that is anything other than e, you have 5 to the x squared or 3 to the 5x minus 9, this is the formula that you are going to need to use. I am not going to expect you to memorize this. I will give you this formula on any quizzes or tests. So the formula says if you have a derivative that you need to do of a function that is a to the u, any number raised to a power, the first thing you do for the derivative is just write down what you were given. Doesn't matter what it was, just write it down. The du dx means do the derivative of the power. And then you take that times the natural log of the base. If it was 3 to the x squared, then you write natural log of 3. To show you how to put this formula into practice, we're going to start with a very, very basic exponential function of y equals 4 to the x. To find this derivative following that formula, the first thing that you do is just write down the function you were given. So it's going to be 4 to the x. Now, do the derivative of the power. The derivative of this power is just 1. Then you take it times the natural log of the base of the exponent. The base of our exponent is 4. So we do natural log of 4. We could clean this up just a little bit by taking that 1 out of there. We don't need the times 1. So 4x times the natural log of 4 is our answer. On example B, our function is f of x equals 7 to the power of 3x squared minus 5x. So to do this derivative, remember that the first thing that you do is just write down the function as it was given to you. So because this is several items, I'm going to put it in a set of parentheses just for readability. 7 to the 3x squared minus 5x. Take that times the derivative of the power, which is 6x minus 5. And then finish by taking it times the natural log of the base of the exponent, which is 7. There is nothing that you can do to clean this up. That is your answer. You're done. On example 3, we are asked to find the equation of the tangent line to the function at the point 0, 0. As soon as I see this equation of the tangent line phrasing, that tells me that I need the derivative because I need the slope of the tangent line, and that comes from the derivative. The next thing I need to notice when I look at this function of f of x equals 3x times e to the power 3x squared plus 5x, I need to recognize that there's multiplication between the x and the e to the power, so I need to use the product rule. Putting the product rule into practice here, we're going to take our first, which is 3x, times derivative of the second. Derivative of the second is an e, so we are going to rewrite the e exactly as given, times derivative of the power, which is 6x plus 5. Now, we need to add to that the second exactly as it was given, e to the 3x squared plus 5x, times derivative of the first, which is 3. What comes before the plus sign is term 1, and what comes after the plus sign is term 2. We need to look and see what's in common in those terms. They both have a 3, and they both have the e to the power. So we are going to factor out (3e to the 3x squared plus 5x power). Now this is still your derivative. We're still cleaning up the derivative here. We're going to pull the 3 and the e to the power out front. If I take those two items out of the first term, what's left is the x and the 6x plus 5. If I take them out of the second term, that's everything that's in that term. Remember, you've got to have that placeholder. We took two items divided by themselves. So what's left is a 1. So we now have 3e to the 3x squared plus 5x times 6x squared plus 5x plus 1. And that's our derivative. Remember what we need this derivative for. This is the formula for slope of the tangent line. So we need to find the slope of our tangent line. And the place we want to do that is the point 0, 0. So that means the x variable, which is what we have in our formula, gets replaced by zeros. If we do that, we will have 3e to the 0 times 0 plus 0 plus 1. Remember that anything to the 0 power is 1. So I have 3 times 1, and then in my parentheses I have 1. So the slope of my tangent comes out to be 3. We are not quite done. We want the equation of the tangent. So we're going to go to that point slope format. And y variable minus y of our point is 0 equals, we just said slope is 3. X variable minus x of our point is also 0. Clean that up, we get y equals 3x. Here is the equation of the tangent line. Example 4 says the balance A in a savings account is given by A equals 5,000 times e to the 0.08 t power, where t is in years. Find the rate at which the balance is changing when t equals 1 and t equals 10. The trick on this one is recognizing that when you see rate at which we're changing, that means find the derivative. So we need to find the derivative of the function a equals 5,000 e to the 0.08t. To do this derivative, notice that we have an e in there. We also have a coefficient of 5,000, so we're just going to keep the coefficient like always. Now, do the derivative of the e. Derivative of e is to write it down as given, and then take that times the derivative of the power, which will be 0.08. We're going to clean this up by taking 5,000 times 0.08, and that will give us 400 e to the 0.08t. So in this case, this gives us the formula for rate of change. Our questions, we actually have two of them. Question 1 says, find the rate of change when t equals 1. So we're going to put 1 into that derivative. We're going to find a prime of 1. We're going to have 400 e to the 0.08 times 1, or 400 e to the 0.08. Put that into your calculator and you will get $433.31. It does not ask for this, but let's review what this means. This is not how much is in the account. This is how the account is changing. So the balance is, because this was positive, it's increasing by $433.31 from year 1, which is what we put in, to the next year, year 2. Question 2 asks us to find the rate of change at t equals 10. So a prime at 10 will be 400 e to the 0.08 times 10, which is 400 e to the 0.8 power. If you plug that into your calculator, you get 890.22. Again, this is how the balance is changing. So the balance is increasing $890.22 from year 10 to year 11. Example 5 says, because of lack of promotion, the yearly sales of a product decline according to the function f of t equals 3,000 e to the negative 0.80t, where f of t represents yearly sales at time t. We are asked to find, on question A, the rate of change of sales. Remember that anytime you see the phrase rate of change, that means the derivative. It just says rate of change of sales in general. So what that means is that A just wants us to find the formula for rate of change. We need to do the derivative of f. We start out with a coefficient, so we're going to keep the coefficient. Now we need to do the derivative of an e, so we're going to keep the e as is, negative 0.8t, times the derivative of the power, which is negative 0.8. I'm going to clean this up by multiplying the 3,000 and the negative 0.8. That will give me negative 2400 e to the negative 0.8 t power. So this is our formula for rate of change. Question B says to find the rate of change of sales at t equals 0.5. Now that we are given an actual number for t, we are going to substitute that into the derivative that we already found. So we're going to do f prime of 0.5. That will give us negative 2400 times e to the negative 0.8 power times 0.5. That makes our power into negative 0.4. Put this all into your calculator and you will get negative 1608.77. What this tells us is that sales are decreasing $1,608.77 from 0.5 of a year to 1 year. Example 6 says the projected Hispanic population in the United States in millions can be approximated by the function h of t equals 37.79 times 1.021 to the t power, where t equals 0 corresponds to 2000, the year 2000, and zeros less than or equal to t's less than or equal to 50. That means that this function only works for the years 2000 to 2050. This is all from data from the U.S. Census Bureau. I chose this problem because it gives you real-life data numbers, and you can see that they're not pretty. Now we have two questions. One says, estimate the Hispanic population for 2015. The second says, what is the rate of change of the Hispanic population in 2015? That first question, because it just says, estimate the Hispanic population in 2015, that wants us to just put 15 into the original. So we want to do h of 15. The reason that I know this is it doesn't say anything about rate of change. That's why I know to just put 15 in the original. So we would have 37.79 times 1.021 that we are raising to the 15th power. If you put all that into your calculator, you get 51.61. Notice up in the original problem, it said that this is in millions. So when we get this 51.61, that means there are 51.61 million Hispanics in 2015, approximately. And if you think about it, that makes sense. It wouldn't be just 51.61 Hispanic people in the year 2015. That's nonsense. Now, question 2 asks us to find the rate of change of the Hispanic population. So that means that we need to find the derivative. So looking at our function, to find this derivative, we have a coefficient of 37.79. So we're just going to keep the coefficient. When I look at this function, this is an a to the u type of function. This is where we have anything except e. So we're going to use that second formula. where the first thing you do is write down what you were given, 1.021 to the t power. You take that times the derivative of the power, which is just 1. And then take that times the natural log of the base, which is 1.021. We want to find the rate of change at 15. So we are going to put year 15 into this thing. We're going to have 37.79 times 1.021 to the 15th power. We don't need to write that times 1, times the natural log of 1.021. Do all this in your calculator. You should get 1.07, and remember, this is in millions. So what this means then is that the Hispanic population is, that number was positive, so it's increasing 1.07 million from what year did we put in? 2015 to the next year, 2016.